Hi, it's me, again, talking to you guys, again, for the very last time this school year. It's crazy, but we are actually on the last lesson that I'm going to teach you guys this year. Sad, I know, super sad. Like, words can't even describe how sad we all are. But we're going to go ahead and continue and just finish up chapter 12 with lesson 7. Now, we had to skip a couple of lessons. We went from 12.3 to 12.7, and we had to do this for just looking through the chapter, I had to figure out, what was most important. This is actually going to be a very easy lesson about theoretical and experimental probability. But I decided to cover this lesson because probability is one of those subjects that they just kind of throw at the back of every math textbook. And I felt like it would probably serve you guys better if you learn this stuff. Basic probability, and this might be something that you might use in a statistics class someday in the future. So our objective today is to find theoretical and experimental probabilities. And this is an interesting word because probability, there's no likelihood with probabilities. It might happen, it might not. And this is something that I'm sure that you guys are obsessed with, a probability of something happening. Well, will I ever, will I ever have my own car? Well, probably, because we're in Southern California, but it's not 100% certain. And when it comes to probability, we want to kind of focus on, what are the chances that something would happen? Now, it's pretty easy to actually figure out, especially basic probability. The probability of an event, or P of the event, meaning the probability of something happening, tells you how likely it is for that event to occur. And you can find probabilities by reasoning mathematically or by using data collected from an experiment. Now, theoretical probability is the number of favorable outcomes. When they say favorable, what this means is the outcome that you want. Let's say that you are flipping a coin and you're trying to convince your parents to buy you a new phone. And you say, all right, Mom, all right, Dad, person who has money that I don't have. All right, if I flip this coin and it's heads, you have to buy me a new phone. And they're obviously going to say no because it's a terrible thing. All right, what's the probability of that? Well, the favorable outcomes is if you want it to be heads, there's only one option, really. Option 2, or then the number of possible outcomes, you would think it's 2, but probably they're just going to, probability 1 is its heads, probability 2, tails, probability 3, your parent says, get out of here, takes your coin, and then you don't even get to flip it, and then you don't get a phone. All right, so what are the chances that this is going to have? Well, the theoretical probability is 1 out of 2 if you actually flip the coin and they go along with it, or 1 out of 3 because they're probably just going to push you out of the way and take your coin. Now, you can play a bigger game with less probability and do the same thing. Okay, if the next car that goes down our street is red, then you have to buy me a new phone. Now, the probability is lower because there's way more options, because it might not be a car, it might be a truck, it might be a van, it might be an e-scooter. All right, it might not be red, it can be white, it can be blue, it can be gray, it can be black, it can be silver, it can be green, it can be orange. There's a lot of possible outcomes. But in that scenario, there's only one favorable outcome, red car, versus a whole mess of possible outcomes. All right, you following me? Cool. All right, let's go ahead and look at problem number 1. Our solar system's 8 planets, in order from least to greatest distance from the sun, are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You will randomly draw one of the names of the planets to write a report on the planet. What is the theoretical probability that you will select a planet whose distance from the sun is less than the Earth's. So in order to figure this out, we need to figure out, well, how many possible planets are there that have a distance from the sun less than the Earth's? Well, according to this, Mercury and Venus are less than the Earth's distance from the sun. They're closer to the Earth, they're closer to the sun. So that would be 2. And how many possible planets are outcomes that are there for you to draw? Well, there are 8 planets. So in this case, we get 2 over 8 is a probability. And because we can reduce, we must reduce, this is just 1/4. All right. There's a 1 out of 4 chance that you will draw a planet for the report that's closer to the sun than the Earth. That was easy. All right. In problem 1, what was the theoretical probability that you will select a planet whose distance from the sun is greater than the Earth's? Well, greater than the Earth's is going to be Mars, Jupiter, Saturn, Uranus, and Neptune. So according to this, there's 1, 2, 3, 4, 5 planets, and there's 8 possible outcomes. And can this be reduced? Nope. And that's all there is to it so far. All right, so let's go ahead and talk a bit about the complement of an event. And this word should seem familiar. We talked about complements a long time ago when we talked about sets and set builder notations. A complement just kind of means like the opposite, or it's like the missing piece. The complement is something that like fulfills the void that was missing. So, I mean, we don't really have to talk about it all that much. Just kind of know it's like the opposite. All right, like an example would be, what is the probability of something not happening? Well, it's just the opposite. So you'll see this in your homework. It's pretty easy to figure out. You kind of do it the same way that you would do example number 1, NBD. No big deal. All right, let's go ahead and talk about odds, because odds are slightly different. Odds describe the likelihood of an event as a ratio comparing the number of favorable and unfavorable outcomes. So this is a little bit different, because whenever we talked about theoretical probability, we would have favorable over the total possible outcomes. But now we're going to be talking about the favorable outcomes divided by the unfavorable outcomes. All right, so what you want to happen compared to what you don't want to happen. Okay, so let's go ahead and look at problem number 3. What are the odds in favor of the spinner landing on a number greater than or equal to 6? So here we have like a classic little spinner that you see at your family board game box for like Chutes and Ladders or something like that. And if you spin the thing, all right, it's going to fall on one of these options between 1 through 8. And they're asking, what are the odds in favor of the spinner landing on a greater than or equal number to 6? So according to this, how many favorable outcomes are there where it can land on a number that's 6 or greater? 1, 2, 3. So total favorable outcomes is 3. And how many do we not want it to land on? Well, unfavorable, so we'll say unfavorable would be 1, 2, 3, 4, 5. And that's it, 3 to 5. There is a 3 to 5 chance that you'll get a number that is greater than or equal to 6. Okay, let's look at Got It question number 3. And they're asking, what are the odds against? Now this is a really important thing, because notice they are saying what are the odds of it going against this thing. So when it says against, we are actually going to flip the ratio around. Whenever we have the word against, we're going to put the unfavorable on top, unfavorable, and we're going to divide it by the favorable. And again, this is what you want to happen versus what you don't want to happen. Think about this like when you're playing a board game with like a family member or a friend, because you obviously play board games still. And like you're gonna win as long as they don't draw a 3, right? No threes, no threes, no threes, right? And then, of course, you think, well, what are the odds it's going to happen? Well, usually it's pretty good because it's going to happen against me. I'm so unlucky, and blah, blah, blah. But really, all right, we can get the odds this way. So what are the odds against the spinner landing on it? Well, we want to figure out, well, the favorable thing is going to be a number less than 3. So how many numbers are here less than 3? Well, numbers less than 3 are, there's only 2 of them, 2 and 1. So the favorable, or what you expect to happen based off of numbers less than 3, all right, is going to be 2. And how many other possibilities are there? 1, 2, 3, 4, 5, 6. There are 6 different options where it can be can go against numbers less than 3. And this just reduces to 3 to 1 odds or 3 to 1. All right, more than likely we'll see fractions, or I guess just 3. But we'll keep it as a fraction. We'll keep it. All right, even though it's the same thing, we'll leave it as a fraction because we're talking about odds and ratios. So I guess that makes sense. All right, now we're going to go ahead and try to talk about experimental probability. Experimental probability, as indicated in problem 4, is the number of times the event occurs divided by the number of times the experiment is done. And if you think about this logically, you know what? This is just straight up a percentage. It's not even anything crazy. All right? Like in this case, after receiving complaints, a skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds no defects in 992 of the 1,000 skateboards. What is the probability that a skateboard selected at random has no defects? So we want to figure out how many had no defects compared to how many were examined. Well, if you just go ahead and take 992 divided by 1,000, you'll get 99.2%. All right, so this probability could be expressed as a percentage or a decimal or a fraction because they're all the same thing. We want percentage for these ones. All right, so really nothing too crazy. Nothing too crazy. All right, so let's go ahead and look at got it question number 4. Suppose the manufacturer in the other problem instead inspects 2,500 skateboards. There are 2,450 skateboards with no defects. So what is the probability of a skateboard selected at random has no defects? So we want no defects divided by the total that were inspected. So there were 2,450 divided by 2,500. And if I just go ahead and divide this with a calculator, 2,450 divided by 2,500, you're going to get 0.98, which is just 98%, which makes sense, right? There's a large probability, a large possibility that we are going to have a no defect skateboard selected. What would the percentage be that we find one that has a defect? 2%. All right, the last question we're going to go over is another probability question, but you can solve this actually using an old method that we have grown to love and utilize. All right, you ask 500 randomly selected households in your town if they have a dog. So there are 500 households. All right, and there 197 have dogs. All right. What we're going to do is we're going to set up a proportion. If you know that there are 2,400 or 24,800 households, how many dogs? How would we solve this? Butterfly method. Yes, our good friend butterfly method makes one more flutter into our heart. All right, if you go ahead and multiply the two numbers across and then divide by the other number, 500, you get 9,771.2 dogs. I don't want to know what 0.2 of a dog is, so we're just going to round it to a whole number. All right, that's it, guys. It's been real. I love being your teacher. That's it. Bye. Peace.